All right, so this lesson will be on exponential functions, and most of the PowerPoint slides I'm using for this short presentation is from Shauna Hader. I use a lot of her PowerPoint presentations because she created really good ones. But we're going to talk about exponential functions, and exponential functions are functions basically based on the graph y equal to b to the x. I'm using b instead of a. Some people use a. The key is the variable is in the exponent. When we were doing polynomials, the variable was the base and the exponent was a constant. But in exponential functions, the variable is in the exponent and the base has to be a positive number other than 1. So an exponential function is a function of the form y equal to b to the x, where b is a positive number and b isn't 1. The reason we need it to be a positive number is we need answers to always be giving us, when we put in inputs, we get answers. So we want a continuous domain. Because if we have the base not being positive, some negative exponents won't work. If you raise negative 2 to the power 1/4, you will not get a real number answer. So we have to specify that. And the reason we don't want b to be 1, we don't want the base to be 1, is 1 raised to any power is what? 1. That makes it very boring. And one of the things we want is for exponential functions to be invertible, which means they have to be 1-to-1. So we need the base to be positive and a number other than 1. So here's the formal definition here. An exponential function f, this is the basic exponential function. An exponential function f with base b is defined as f of x equal to b to the x, or you could say y equals to b to the x, where b is a positive constant other than 1. Here are some examples. F of x equal to 2 to the x. G of x equal to 10 to the x. In this case, the first case, 2 to the x, the base is 2. 10 to the x, the base is 10. H of x equal to x, 3 to the x plus 1. That's another exponential function that has just been transformed, right? They modified the x part. The base can be a fraction. J of x equal to half to the power x minus 1. So that's another exponential function. On the other hand, these other ones down below with the capital letters are not exponential functions. In this case, f of x equal to x squared is not an exponential function because what? Why isn't this an exponential function? Well, the variable is in the denominator, is in the base, it's not supposed to be in the base. What about this guy here? 1 to the x. Now your answer matters, right? The base can't be 1. This is just the line y equal to 1. It's a horizontal line. And what about this one here? H of x equal to parentheses. The base has to be positive. By the way, if I had put a negative in front of this 3 without it being in parentheses, or a negative in front of this 10, that would be fine. That would just be a transformation, because that would just be negative 1 times the quantity 10 to the x. But if I put the negative 1 in parentheses, as I do here, I'm saying I'm raising negative 1 to the power x, and that will not be an exponential function, because the domain of this function is really messy. All right, it's horrible. What about this guy? Variables are both. This is a weird function. This only works when x is positive. Well, nicely when x is positive, but even so, it's not an exponential function because the base cannot be changing for an exponential function. All right. So exponential functions look like the ones on top, but not like the ones at the bottom. So let's take a quick look at a few things. With an exponential function, there are some nice things about them that we like. Of course, remember the base is a constant and the exponent is where the variable occurs. So let's plot a few points here. We plug in 3, we get 8, right? 2 to the 3 is 2 times 2 times 2. What do we get when we plug in 2 for this function? 4. And then when we plug in 1, 2 to the 1 is 2. And then 2 to the 0, 1. In fact, any non-zero number raised to the power 0 gives you 1. So exponential functions in this basic form will always pass through what point? 0, comma 1. In other words, the y-intercept would be 1, which is nice. You keep going. If you plug in a negative number, do we get a negative answer? No, because the exponent is negative doesn't make the expression negative. All you're doing is just flipping numbers, right? If you flip a positive, you get a positive. Will we ever get a negative answer then? No. So in basic form, exponential functions do not give you a negative. When I say basic forms, I mean simplified y equal to b to the x. I'm not talking about transformations. So one of the things we notice here with exponential functions, they can get smaller and smaller and smaller and smaller, but they will never get negative. Will they ever get to 0? No. Therefore, we have ourselves a horizontal asymptote. As you go further and further to the left, which just means as x approaches negative infinity, the y values get closer and closer to 0. We say y approaches 0. Horizontal asymptote, but it will never get there. So exponential functions, even though you can plug in all x values, you won't get all possible y values. You will only get positive outputs. I'm talking about the basic exponential function here. And that allows us, this is another version of the graph that you can see in nicer detail. I took this out of a textbook, Pre-Calculus by Blitzer, section 3.1. So, fifth edition is an older edition of the book. But as you can see, the domain is all real numbers, negative infinity to infinity, and the range is only positive real numbers. From parentheses 0 to infinity, not bracket, because you can't get 0 either. So it's all positive, not simply non-negative, only positive outputs. Are you with me, everyone? This is very important because when we talk about logarithmic functions, that's gonna matter. Let's move on to a little bit more information here. Let's talk a little bit about the properties of the graphs of exponential functions. Now, in this little set of properties I'm going to list out, I'm going to talk about the base where the base is bigger than 1. But there's a little nuance where the base is smaller than 1, which I will point out in a few minutes. Now, the best way to remember these properties is to know what the graph of an exponential function looks like. When the base is bigger than 1, the graph looks basically like this brown graph, or this blue graph, or this red graph. These are 3 different versions. You notice they generally have the same shape, right? It's just like some of them are steeper than others. The bigger the base, the steeper the graph gets after you've crossed the y-axis. But they all are generally starting low and then going upward, increasing functions. So once you remember that graph and that they cross through the line, the point 0, 1, that will help you to remember a lot of the properties. For example, look at the graph here. What is the domain of this function? What x values can we plug in? Is there any restriction? Huh? Well, we can get 1. I'm asking for domain restrictions. Is there any x values that you plug in and you do not get an answer? So what's the domain? Negative infinity to infinity. So the domain is all real numbers. Negative infinity to infinity is how I prefer it. What about the range? Look at the graph. We just said it. What's the lowest y value? Just above 0, right? Never actually gets to 0. How high does it go? To infinity. So the range is 0 to infinity, parentheses, only positives. You do not get 0. So since you do not get 0, do we have any x-intercepts? No. Right, no x-intercepts because you do not touch the x-axis. You cannot get 0. So there are no x-intercepts for the exponential function. And you can see that property from the graph. If you remember the graph, those 3 properties work. By the way, these three properties we just listed, and the 4th one we're going to list right now, apply to any exponential function of the form b to the x, whether the b is bigger than 1 or smaller, between 0 and 1. It's the same properties. Where does it cross the y-axis? What's the y-intercept? 0, 1, because 2 to the 0 or 3 to 0 or any non-zero number to the power 0 is 1. So the graph crosses the y-axis at the point 0, 1. These four properties apply to all basic exponential functions as long as the base is bigger than 1, bigger than 0, which is all basic exponential functions. So if you're talking about a basic exponential function with a positive base other than 1, these four properties apply. The next property is only if the base is bigger than 1. The graph is increasing. It's going upward from left to right. If the base is smaller than 1, it's going to be reversed. We'll see that in a few minutes. It's going to be going the opposite direction. But same basic shape. It's like a mirror image across the y-axis. And then the next property also applies, but it's different from, in a sense, from different for bases smaller than 1 than bases bigger than 1. That is, the graph has a horizontal asymptote, namely the x-axis, the line y equal to 0. However, when the base is bigger than 1, the asymptote occurs as x approaches negative infinity. That means as you go to the left, it levels off. But as you go to the right, it rises. It's the opposite when the base is smaller than 1. So that's why there's a little nuance for the sixth property here. But those 6 properties are key properties of exponential functions that you need to know, and you can tell most, if not all, of those properties from knowing the graph. Something else I want to point out about the graph is the bigger the base, the steeper the graph gets after you cross the y-axis, which makes sense. If you raise a number, if you have a number and you raise it to a positive power, the bigger the number, the bigger the answer, right? If I raise 2 to the power 3, I get a smaller number than if I raise 5 to the power 3. 2 to the 3 is 8, 5 to the 3 is 125, yeah? And even if you do a decimal or a fraction, if I say what is 4 to the 1/3, well, yeah. 2 to the 1/3 is the cube root of 8. Yeah? That's like 1 point something. 4 to the 1/3 is the cube root of, let's say cube root of 8. 2 to the 1/3 is the cube root of 2, sorry. 4 to the 1/3 is the cube root of 4. Which one is bigger? The cube root of 4 or the cube root of 2? Cube root of 4 is bigger. Because you need a bigger number to cube it to get 4 than you do to get 2. So even if you're talking about rational exponents, as long as you raise it to a positive exponent, the bigger the base, the bigger the result. So for the same x input, the bigger base will give you a bigger y input, y output. So as the base gets bigger, the graph gets steeper after 1. It rises rapidly. You ever heard of exponential growth? Yeah, this is what they're basing it off. And it has a lot of applications, which we'll cover in another lesson. Transformations of functions apply here. All the transformations we did in transformations of functions apply. So vertical shift, horizontal shift, reflection across the x-axis, reflection across the y-axis, vertical stretch, horizontal stretch, they all apply just as with regular functions. So if you add to the x's, that means if you add to the exponents, you're going to shift to the left if you add a positive to the exponents. If you subtract from the x to the exponents, you shift to the right. If you add to the whole expression, that means you don't add to the exponents, you add it to the function itself. Then you shift upward, and if you subtract, you shift downward. If you multiply the exponent by -1, then you reflect across the y-axis. But if you multiply the whole expression by -1, then you reflect across the x-axis. And of course, if you multiply the exponent by a constant, then you're going to have either a horizontal compression or stretch, depending on what the constant is. And likewise with multiply the whole expression by a constant. So it's the same stuff as we did before. Here are a few examples. This is the graph of 2 to the x. What does the graph of 2 to the x plus 3 look like? What will happen here? Shift it where? Up. How much? 3 units, because we're adding the 3 to the whole expression, so we're adding to the y's. Now, whenever you shift a graph, the asymptotes shift as well, right? So the horizontal asymptote here is going to shift what direction? Upwards. The original horizontal asymptote was the y equal to 0. What's going to be the new horizontal asymptote? Y equals 3. So there will be a horizontal asymptote right there. What about this example? Y equal to 1 minus 2 to the x. How many transformations are we doing here? 2. What are they? Reflection across the x-axis because there's a negative in front of the whole thing. And then what are we doing? Up 1 because it's actually plus 1. Yeah? You can think of this as negative 2 to the x plus 1. And that negative is not, the base is not a negative. You're multiplying the expression by a negative 1. The base expression. So we flip it over. That's where that dashed red line comes in. And then we shift the whole thing up. What's the new asymptote? Y equals to what? 1, because it shifted the graph up and the asymptote gets shifted as well. This one. What are we doing with this graph? Y equal to 2 to the x minus 2 minus 1. That's correct. We're shifting the graph to the right 2 units and then down 1 unit. Actually, it doesn't matter which one you do first, but same effect. But that's correct. So what happens to the asymptote now? So what's the new asymptote? Y equals negative 1. That's correct. You gotta remember. So I'd like you to try these. Gonna give you a few minutes to try them, and then we will take a look at the results. That's a few minutes. I'm gonna give you 1 minute to try it. Don't need more than a minute. All right, so let's take a look at what we have here. Which graph is our basic graph? Number 22. So that goes with which function? The lowercase f of x equal to 3 to the x. And let's just put a few details here. The graph here has y-intercept. What's the y-intercept for that graph? 0, 1. And it's also an increasing graph, right? And of course, the rest of them have some variation of that. This one is it's just like the reverse of this, right? So we know these are all other transformations of this. So this function number 22 is f of x. Where can I put that? F of x equal to 3 to the x. I want to put it somewhere where it's not going to be confused with the other graph. F of x equal to 3 to the x. Ooh. Let's do this. Little carve out right there. F of x equals to 3 to the x. All right, good. So let's start going through now. So we have lowercase f of x covered. So number 19. What did we do with number 19? What do we do with number 22 to get number 19? We reflect it where? Both axes? Yeah. All right, so we flipped it across the x-axis and across the y-axis, huh? So that's what those arrows indicate. Let me probably write it in right here. Create a little carve out space here. Reflect over x and y axes. Is there anything else that we did? No, we didn't do anything else. So which graph is this then? Which one of the H's, capital or lowercase? Capital H, that's that one there, because those are both negatives because of reflection. So we say h of x equal to negative, that's the one that told us to flip it vertically, that's over that way. 3 to the negative x, that's the one that told us to flip it horizontally, to reflect it horizontally. Good. What about number 20? What does it look like we did with number 20? We shifted it to the right, so it went from, the intercept went from 0, and that point there now is at 1, 1. So the graph moved from 0, 1 to 1, 1. So we shifted the graph to the right 1 unit. What graph shows a horizontal shift? Lowercase g of x. Do we all agree with that? So it's lowercase g of x is equal to 3 to the, and since we're doing a horizontal change, we modify the x's. 3 to the x minus 1. Number 21, what do we do with, okay, what's going on here? Okay, what do we do with number 21? What do we do with the graph of f of x to get number 21? Reflect across the x-axis, that's it? All right, so which capital F of x? Yeah, we're only doing a vertical transformation. So f of x is equal to negative 3 to the x. So I'm trying to write this properly here. Reflect over the x-axis. All right, we already have number 19, number 22 down. Number 23, what does it look like we did for number 23? Down how much? 1 unit. So down 1 unit. So which function indicates a shift downward of f of x? Which one? Lowercase h of x. So I guess I can squeeze it in right here. H of x is equal to 3 to the x minus 1. Yeah? And then, of course, the other one, what did we do for the other one? Reflect it over the y-axis. That's a horizontal motion. So if it's a horizontal change, we're adjusting what? We're adjusting the x's, which is in the exponent. So my new equation will become, well, 3 to the negative x, yeah? Any questions about this? Alrighty, so let's move on here. Now, we saw one of the reflections, one of the transformations that looked similar to this one, 2 to the negative x. We did 3 to the negative x. And that was a horizontal transformation, a reflection across the y-axis, yeah? Here's the thing though, using properties of exponents, we can see that this links up to something specific, which is very important. If you look at the graph, the blue graph is the original graph, y equal 2 to the x, and the red graph is the reflected graph, y equal 2 to the negative x. Yes? Exponent rules, however, tells us something important about a negative exponent. If your exponent is negative, you're really dividing. So 2 to the negative x is 1 over 2 to the x, 1 over 2 to the x, which is half to the x, because 1 to any power is 1. So in reality, if the base is a fraction smaller than 1, it's kind of just a reflection of one of those other graphs. It's like a transformation of the other graph. A base smaller than 1 is a reflection across the y-axis of a corresponding graph whose base is bigger than 1, like the reciprocal of that number. So that's why when the base is bigger than 1, the graph is increasing, but when the base is smaller than 1, the graph is decreasing. So for example, if the base was 4/3, the graph will look similar to the blue graph here. But if the base is 3/4, the graph would look similar to the red graph. So that means when the base is smaller than 1, that means the base is between 0 and 1. Remember, the base can't be negative, base can't be 0, the base can't be 1. But if the base is smaller than 1, something between 0 and 1, then the basic graph would look like this, the red graph here. But if the base is bigger than 1, as we said before, the graph would be increasing. They'll still cross through 0, 1. The horizontal asymptote will still be the x-axis, although for different sides. And their steepness will be the same, but it's just that one is rising on one side and one is rising on the other side. So this is just a little graph that illustrates what I just said about half to the x. Half to the x looks like 2 to the x just reflected across the y-axis. So we have some additional properties here that we need to remember. These are the same properties we listed with the modification for the base smaller than 1. So again, remember what the graph looks like, and you can remember most of the properties. Domain is the same, range is the same, but if the base is bigger than 1, graph is increasing like the blue. Base is smaller than 1, graph is decreasing like the red. The function is 1 to 1. And still has a horizontal asymptote, but on different sides of the axis. And here's a further illustration with some graphs here. 7 to the x is the green graph. This black graph is 2 to the x. Half to the x is 2 to the x, like a mirror image of 2 to the x. 3/4 to the x is, decreasing. And then we talk about a special base called the natural exponential base. This is one of our favorite numbers in mathematics. Most mathematicians love this number, including me. I'm not a mathematician, but you get the idea. E is a spectacular number. It's so lovely. So lovely. So here's how E comes up. It's like you take simple interest and then you do compound interest, and then you just reduce the period of time that you're doing compound interest to a continuous period. I'm doing it loosely here. Remember, simple interest, I equal to PRT, interest equal to principal times rate times time. And basically what it is if you take a certain amount of money like the principal, and you say you lend it to someone and you say, okay, after 3 years, you're going to pay me back with an interest rate of 10% per year. What basically the person does is they take your money. Let's say they take $100 from you. They take the 3-year period. They multiply that 3 years by the 10% per year. That's basically 30%. Find that 30% of the original amount and then add that on as interest to you. So they'll pay you back $130. Are you with me? So the question now is, what if instead of waiting till the end of the time period, you to calculate the interest, you calculate the interest at intervals, like at the end of a month. So you take the 10% and it splits up into 12 pieces, because there are 12 months in the year, and you calculate the interest on that amount after the first month. And then once you get that interest, you add it to the principal. So now your principal is bigger by a little bit. And then at the end of the second month, you do another 1/12 of the 10%. And you keep doing that. After 3 years, the person will owe you more money than they would have before. They will owe you more than 30% of the original. So that's how credit cards work. There's another type called continuously compounded interest, which happens when you take the time period, and instead of doing it like once a month or even once a day, you're doing it continuously. And that's what this E comes in. E says, what if the amount of the intervals you're using are smaller and smaller and smaller? That means you're compounding it more and more and more and more, like infinitely many times. What does that piece there get to? And that's where E comes from. That's the motivation behind E. Not going to go into much more detail about that. That's more covered in a pre-calculus class, or if we had time, which we don't. But E is one of those numbers. It's extremely useful in studying nature. There's a lot of patterns in nature that rely on E. E is a very big deal in calculus. Huge. All right. It's called an transcendental irrational number. Very important. Pi is also an important number, but E is a lot nicer. So how do you find, if you have a TI-83 or TI-84 calculator, the E, on any scientific calculator, look for that LN button. Sometimes the L is lowercase, so it looks like in, but it's actually lowercase ln, all right? We'll talk about what ln is later on, but above the ln, you see e to the power x. That e is this number e. It's a number between 2.7 and 2.8. So 2.718281828. It's an irrational number, so the pattern doesn't continue. It gets weird after that. And so this is just an approximation. So if you have a TI-83 calculator, you can use it to find it. There are actually two places where E occurs. E is also over the division button on this calculator, but different calculators operate differently. Learn your calculator. So if you look at the graph of e to the x now, the graph of e to the x is close to the graph of 3 to the x because 2.7 is pretty close to 3, yeah? But its shape is generally the same. So that's one of the fundamental functions that you'll need to know. Remember earlier we spoke about fundamental graphs, square root of x, cube root of x, 1 over x, those graphs. This is one of those that you need to know as well and learn the properties thereof. All right, let me quickly check something before we go to this last part here. I'm just making sure that I do not overlook anything. Good. All right, so last concept here for this particular part of the lesson, The next lesson will be on logarithmic functions, which are based on exponential functions. This is called the one-to-one function property. Function property says if you plug in the same number, you should get the same answer, right? If you plug in 2, you should always get the same answer. One-to-one property says if you plug in 2 different numbers, you should get 2 different answers. That's what makes a one-to-one function. Let me give you an illustration of a function that's not one-to-one. Y equal to x squared. That's not a one-to-one function. We studied that before. And one of the ways you know is it fails the horizontal line test. The horizontal line test effectively says you plug in 2 different x values and got the same y value. So for example, for the graph of y equal x squared, sorry, if I plug in 3, what do I get as the answer? 9. What do I get if I plug in negative 3? 9. So that indicates if I plug in 2 different x values, I get the same y value at some time, right? That makes the graph not one-to-one. Exponential functions are one-to-one. If I plug in negative 3, I'm going to get a different answer than I would get if I plug in positive 3. If you plug in 2 different inputs, you will get 2 different outputs. That's a one-to-one property, which makes it nice because then we can work backwards nicely with them. And that's what this property is saying here. If a to the u is equal to a to the v, then it's because u and v are the same. If you get the same output, it's because you plug in the same input. That's a one-to-one property. How does that work for us? That allows us to solve certain exponential equations. Here's an example. 2 to the 3x minus 4 equals to 8. I want to figure out what x is. If I can figure out a number such that these two guys have the same base, then I can identify the exponent as being exactly the same, because this rule says if you have a base to a power equal to a base to a power, then the exponents have to be the same. Is there any way for me to get these two to have the same base? And if so, what would that base be? Well, if I multiply both sides by 4, I'm going to have a problem. Can I change one of these two sides? What side would I change so I end up with the same base on both sides? The right-hand side. What would I change the right-hand side to be? 2 to the third. So if I rewrite 8 as 2 to the third, now I have 2 to the 3x minus 4 is equal to 2 to the 3. Same base, so that means these must be the same thing. If they have the same base, positive base other than 1, then the exponents must be equal. So we just set them equal to each other. By the way, I'm not canceling the bases here. I'm just interpreting what this means. A number raised to a power equal to the same number raised to a power must mean the powers are equal. And then I can always just solve for x. So called the one-to-one property. And we're going to use that a bit. Let's try those. So here's how it looks. Steps. Rewrite the two sides of the equation so they have exactly the same base with nothing else hanging on, no coefficients or anything. Set the exponents equal to each other. Solve for the variable. Go ahead and try those three. All right, so let's take a look at the answer to number 1 here. Number 1, 5 to the x equal to 625. What can I do to solve this? That's right, 625 is actually 5 multiplied by itself 4 times, yes? So now that the bases are the same, 5 to the x, both of them are base 5, and 625 is 5 to the 4. Then, since the bases are the same, then the exponents must be equal to each other. I did not cancel anything, I just interpreted the meaning of that expression. And we're done. That was pretty straightforward. Let us try number 2. Can we get them both to have the same base here? Or will we get 3 to the 2x plus 1 is equal to what? 3 to the 3 cubed. Now that the bases are the same, what do I do? 2x plus 1 is equal to 3. So the exponents equal to each other. And then we solve. So 2x is equal to 2. So x is equal to 1. And let's check to see if we're correct. I plug in 1 here. 2 times 1 is 2. 2 plus 1 is 3. 3 to the power 3. 27. Yes, 2 plus 1 is now 1. All right, number 3. What base can we use for number 3? Can we raise 4 to a nice power to get 32? 4 to what power gives you 32? Not 4 times something, 4 to a power. So it's 4 multiplied by itself a certain number of times to get 32. Is that easy? No. So we might have to use a different base. What base could we use instead? 2. How? Two to the 4th is 16. 2 to the 5th is 32. What about the right-hand side? The left-hand side, sorry. Ah, that is correct. 2 to the 2x, because 2 to the 2 is actually 4, yeah? And then 4 is raised to the power x. And then exponent rules say multiply the exponents. So we can just say 2 to the 2x is equal to 2 to the 5. And now we have the same base. Now that we have the same base, we do what? 2x equal 5. Set the exponents equal to each other. And solve for x. X is equal to 5 over 2. And if you want to check this, let me just do a little check in the corner here. You can check this on the calculator. 4 raised to the 5 halves really means the square root of 4 raised to the power 5. Yeah? Exponent rules from intermediate algebra. The square root of 4 is 2, and 2 to the 5 is 32. So it does work. Any questions about this? All right, let's do a few more examples, and then that will be that for this. This one is from the PowerPoint. 4 to the x equal to 1 over 8. What common base should I use for this one? What common base should I use for this? Well, 1/8 is kind of hard to use as a base. Nothing comes to mind? What base, what number could be a base for 4 and for 8? That means you raise that number to a certain power, you get 4. You raise that number to a certain power, you get 8. 2! Sometimes you have to go smaller. So we just did something with this, like this, right? 4 to the x. And we said 4 is 2 squared, and 8 is 2 to the what power? Third. So 1 over 8 is 2 to what power? -3. Yeah, because the reciprocal exponent rules. So 4 is 2 squared, and 1 over 8 is 2 to the -3, because 8 is 2 to the 3, and the reciprocal means negative exponent. Yes, you got to know your exponent rules. For those of you going into calculus, whether it's business calculus or calculus 1, yeah, that stuff is particularly important. So we multiply the left side exponents because of exponent rules, you know. Raise something to a power, you multiply the exponents. So we get 2 to the 2x equal to 2 to the -3, and then we do what? So the exponents equal to each other. Solve for x equals to -3/2. And we can always, you know, check. 4 to the -3/2. Let's see what we have. That means that's 1 over 4 to the 3/2. 4 to the 3/2 means the square root of 4 cubed. And when you do the square root of 4, you get 4. You get 2. And when you cube it, you get 8. Or if you cube 4, you get 64. Square root of 64 is 8. And it's in the denominator. So let's see if we can try a few questions here. And that will be the last for this. I will give you a moment to do these, and then we'll go through the answers. All right, so let's take a look at number 4. Number 4, 125 to the x equal to 625. What answer did you get? X equals 2. You get x equals to what? Uh, 125 squared doesn't give you 625. X equals 4/3. How did you 4/3? How did you get that? Base 5, right? So 5 to the power 3 x, and yeah, I mean, I don't need to do it this year. You could see that step is 3x, right? And then 625 is 5 to what power? 5 to the 4th. See, it's not easy to get 125 raised to a power to get 625. So we end up with 5 to the 3x is equal to 5 to the 4, which means what? Which means 3x is equal to 4, and that means x is 4/3. That's it. Don't use decimal answers, by the way, if at all avoidable. That's that. Looks so easy. What about number 5? What do we do for number 5? So we have 5 to the 2 minus x is equal to 5 to the negative 3. Then what do we do? So the exponents equal to each other. 2 minus x is equal to negative 3. Subtract 2 from both sides, so get negative x is equal to negative 5. Solve for x is equal to 5. So easy. So easy. Number 6. What base are we using for number 6? 7. So I have 7 to the exponent x minus 2 over 6. And what about the base? What about the right hand side? What square root of 7 actually is what? 7 to the 1/2. So therefore we have x minus 2 over 6 is equal to 1/2. What do I do to get x by itself? Multiply by 6. If I multiply both sides by 6, I get x minus 2 is equal to what? Equals to 3. And then what do? Add 2 to both sides, x equal to 5. And it makes sense. You plug in 5 up here, you get 5 minus 2 is 3. 3 over 6 is half. 7 to the half is square root 7. Number 7, what are we doing for x? Well, for the base. What base are we using for number 7? Base 3. So this thing here, 9 to the x is really 3 to the what power? 3 to the 2x. What about the right hand side? 1/3. Because cube root is to the 1/3. Yeah? So I'm just going to write that intermediate step there. And I'll just write this intermediate step here as well. And now we see that 3 to the 2x is equal to 3 to the negative 1/3. What do I do with that? 2x equals to negative 1/3, which means x is equal to what? Divide both sides by 2, which means multiply the denominator by 2. So what's the answer going to be? Negative 1/6. Number 8. Number 8. So we use 2. So it's 2 to the 3rd raised to the power 1 minus x. I'm going to put that 1 minus x in parentheses. Well, I'll put it in parentheses the next step. What about this side? The right side? 2 to the 2 to the x plus 2. What do I do now? Yeah, I can multiply and distribute the exponents. So I'm going to do it this way. 3 times 1 minus x is the exponent for the left side. And 2 times x plus 2 is the exponent for the right side. Right? And then what do? So the exponents equal to each other, and we can distribute at the same time as well. The operations do not interfere with each other. And this becomes a simple linear equation in one variable. 3 minus 3x is equal to 2x plus 4. Yeah? And we can solve for x. I'm going to subtract 3 from both sides and subtract 2x from both sides. So that means negative 5x is equal to 1. So x is equal to negative 1/5. This one is actually pretty easy. It's just the exponential base e. We already know what the base is. What is the base? E. So how do I rewrite this so I can solve it? E to the power x plus 4. E to the power negative 2x. And I would recommend you say to the, so that you know it's an exponent, not a multiplication or base. So e to the x plus 4 is shorthand for e to the exponent x plus 4. And e to the negative 2x is e to the power negative 2x. So what do we have here then? X plus 4 is equal to negative 2x. And then we solve. Subtract x from both sides. X is equal to negative 4/3. We good? Of course, you need to practice, and a good place to practice is Khan Academy. Khan Academy, and I told you about the OpenStax app. I don't know if anyone has been using it. OPENSTAX, and you can go to the website openstax.org. They have the college algebra textbook on the website. Not ours, but a college algebra textbook. Khan Academy as well. Make sure you're watching those videos and doing those exercises and assignments on Khan Academy to help you be prepared for this. Practice.